In this video, we're looking at other methods of proof. Here we've got proof by exhaustion. So when we're doing a proof by exhaustion, we are trying different possibilities, and if all the possibilities are covered, then we have proved it. So a simple case, prove that when n is an integer and n is bigger or equal to 1 and less than or equal to 4, n squared minus n plus 11 is prime. So we're just going to try every possible number. So when n equals 1, we're going to have 1 squared minus 1 plus 11. 1 minus 1 is nothing, plus 11 is 11, and that is prime. When n is 2, we'll have 2 squared, which is 4, take away 2, which is 2, plus 11, that will give us 13, and again 13 is a prime number. When n is 3, 3 squared is 9, take away 3 is 6, 6 plus 11, 17, and again we have a prime number. And finally, when n is 4, 4 squared is 16, take away 4 is 12, 12 plus 11 is 23, which is another prime number. So that's all the possible numbers that we can have. They all give an answer that's prime. So we can say when n is an integer and it's between 1 and 4 inclusive, n squared minus n plus 11 is prime. One for you to try, so give that one a go. So again, we're just going to try all the different numbers. So when n is 1, 1 squared minus 1 is 0, plus 5 is 5, which is prime. When n is 2, 2 squared is 4, take away 2 is 2, plus 5 is 7, which is prime again. When n is 3, 3 squared is 9, minus 3 is 6, plus 5 is 11, and again 11 is a prime number. And finally, when n is 4, 4 squared is 16, take away 4 is 12, 12 plus 5 is 17, and that is a prime number. So therefore, when n is an integer and between 1 and 4, n squared minus n plus 5 is prime. Here's a much more complicated example. So it's still proof by exhaustion because we're still splitting up our proof into different examples, different cases. So prove that all cube numbers are either a multiple of 9, one more than a multiple of 9, or one less than a multiple of 9. So let's think of the cube numbers. 1 cubed is 1, 2 cubed is 8, 3 cubed, 4 cubed, 5 cubed, 6 cubed is 216, and so on. So we have, well, one more than a multiple of 9. Well, one more than 9 times 0. One less. 8 is 1 less than 9. And then we've got a multiple of 9 for 27. 64 is 1 more. It's 1 more than 63. 125 is 1 less. 1 less than 126. And then 216 is a multiple of 9 again. The quick way of telling if a number is a multiple of 9 is adding up the digits. So 2 plus 1 plus 6, that equals 9, which is in the 9 times table, so it's a multiple of 9. And the same with 27, 2 plus 7 is, they add up to 9. I know 125 is 1 less, because 1 plus 2 plus 6, 126, adds up to 9. So that is in the 9 times table. So we've got 3 different cases. So we've got, it repeats every 3. 1 more, 1 less, multiple of 9. 1 more, 1 less, multiple of 9. So we're going to use the 3 times table. So we're going to say a number can either be in the 3 times table, 1 more than the 3 times table, or 1 less than the 3 times table. Or we could say 3 times table, 1 more than the 3 times table, and 2 more than the 3 times table. Either way, we're just using the 3 times table for this question. So we're going to do 3. We're going to do it 3 times. So we're going to do 3n. We can do 3n plus 1, and then either 3n minus 1 or 3n plus 2. It doesn't matter which we do. Either way, let's do 3n minus 1. Either way, we will cover all the cases. So every number is either 3n, 3n plus 1, or 3n minus 1. So let's start with 3n. So for 3n, it's a cube number, so 3n cubed is 3 cubed is 27, n cubed is n cubed, so 27n cubed. And it's a multiple of 9 because it can be written as 9 times 3n cubed. So multiple of 9. For 3n plus 1 cubed, so it's 3n plus 1 times 3n plus 1 times 3n plus 1. So we're going to expand and simplify. So that would be 9n squared plus 3n plus 3n, so plus 6n plus 1, the first 2 brackets. And then expanding again, we've got 27n cubed plus 9n squared plus 18n squared plus 6n plus 3n plus 1, which is 27n cubed plus 27n squared plus 9n plus 1. So this is going to be 1 more than the 9 times table, because I can take 9 out of the first 3 terms, and then there'll be a plus 1 on the end. So that's 1 more than a 3 times table, the 9 times table. And for 3n minus 1, so we've got 3n minus 1 cubed, which is 3n minus 1 times 3n minus 1 times 3n minus 1, which would be 9n, the first 2 brackets expanded, would be 9n squared minus 3n minus 3n plus 1, and then that's times 3n plus 1 again. So expanding again, 27n cubed minus 9n squared minus 18n squared plus 6n plus 3n minus 1. So that is 27n cubed minus 27n squared plus 9n minus 1. If I factorize now 9 out of the first 3 terms, it's 1 less than the 9 times table. So now we could just write a concluding statement to say all cube numbers are a multiple of 9, one more than a multiple of 9, or one less than a multiple of 9. One for you to try. Prove that all square numbers are either a multiple of 4 or one more than a multiple of 4. So this time we have square numbers, and there's only 2 possible outcomes. So it's going to repeat every other time. So the square numbers, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, and so on. So we can see all the even ones are multiples of 4. And then all of the odd ones are one more than a multiple of 4. So all numbers are either even or odd. So there are 2 options this time. So our proof by exhaustion, we're going to try even, try odd, show that in both cases it's true, or there's one for each case, so therefore it's true. So let's try even. So an even number we can write as 2n. So I'll just write even here, 2n, and we're going to square it. So 2n squared is equal to 4n squared, which is a multiple of 4. So when we have an even number, it's a multiple of 4. For odd numbers, an odd number we can write as 2n plus 1. So 2n plus 1 squared is 4n squared plus 2n plus 2n plus 1. So it's 4 times n squared plus n plus 1. So that's 1 more than a multiple of 4. So all square numbers are either a multiple of 4 or one more than a multiple of 4. Find a counterexample to disprove that when n is an integer, n squared minus n plus 11 is always prime. So this is called disproof by counterexample. So if we can find a number to put in for n that shows that it's not prime, if we can find a number for n that makes n squared minus n plus 11 not a prime number, then we've disproved that it's always prime. So we just need to find a number that makes this not a prime number. So we know 1, 2, 3, and 4 make it prime. How about 5? So 5 squared minus 5 plus 11. $31. So that is a prime number. How about 6? That's 41. And again, prime number. 7. $53. And again, prime number. If I press shift fact on the calculator, it writes it as a product of its prime factors. So until I found something with two factors, apart from one itself. So 8 squared minus 8 plus 11 is 67, which is prime again. How about 9 squared minus 9 plus 11? 83, which is prime again. 10. 101, that's prime. 11. 121, there we go. So if I press shift fact, it's 11 squared. So 11 squared minus 11 plus 11 is 121. 121 is 11 times 11, therefore not prime. And therefore, n squared minus n plus 11 is not always prime. So we've disproved it. It's not always prime because when we put in 11, it is not a prime number. Find a counterexample, one for you to try. So this time, if we put in 5, 5 squared minus 5 plus 5 is going to be 25. 25 is 5 squared, 5 times 5. Therefore, it's not a prime number. And n squared minus n plus 5 is not always prime.